This is Armin. I'm Maciej, and we're going to talk about PyPy. Who have heard about PyPy before? Okay, so some people. There will be something new for everyone, so we'll hope it goes fine. So who we are? I joined PyPy around 2007 through Google Summer of Code. I've been working on PyPy pretty much ever, doing various things like garbage collector and just-in-time compiler, beat everything. Armin started PyPy. Before PyPy, he did Psycho. Who has heard about Psycho? Okay, Psycho used to be this crazy hack that took a normal CPython VM and compiled bytecode to assembler on the fly, and it kind of almost worked, except sometimes it didn't. So he decided to abandon it and create PyPy instead. We started last year a consulting company called Baroque Software, where we offer benchmarking and various stuff. I'll talk about that a bit. What is PyPy? So, well, can you show the demo of PyPy? PyPy is just a Python interpreter. So you run it pretty much like CPython, except it has 4 arrows instead of 3. And yes, more is better. You can do some stuff like, yes, well, addition works. Well, imports Python, I guess. Python is a benchmark that comes included in Python standard library. So normal Python, I think, clocks around 100,000, something like that. I don't know. Well, run it again. Up. And now the second time is about 4 times faster. And as you can see, the original author didn't consider 6 digits or 7 digits here. So the scientific notion really makes absolutely no sense here. So what happened here is that the first time it ran like normal interpreted mode, and the second time it ran with the JIT. So it compiled pieces and bits into assembler and ran it faster. So this is pretty much it. PyPy is a Python 2.7 interpreter and has beta support for 3.2 and 3.3. And among other things has a just-in-time compiler that generally makes stuff run faster. That's end of story. I can just walk out. This is what it is. We wrote a Python interpreter. It's faster. Benchmarks. Those are benchmarks. Everybody loves benchmarks. So on the x-axis are various programs ranging from absolutely tiny. I think this function is like 5 lines of code, to stuff like Twisted, which is not tiny at all. And it's all relative to CPython. So CPython, it's 2.7.2, but CPython really didn't change performance all that much. So 1 is CPython, the lower the better. So on, say, AI, it's 17% of the time of CPython. So as you can see, it really depends on the benchmark, but generally speaking, it's significantly faster than CPython on most workloads. Demo. We showed the demo. Recently, so we have a pretty tight release schedule. We released a few times a year. We did a ton of improvements. So if you tried PyPy, say, 2 years ago, we did a lot of work in between then and now, including garbage collection improvements, just-in-time compiler, random strange corners of Python standard library. For example, there are people who rely on CSV module being really, really fast. We added ARM support. So PyPy right now supports x86, 32 and 64-bit, and ARM in few flavors. Not all of them, but there are tons. Most recent ARMs should work, and that work was sponsored by the Raspberry Pi Foundation, and we started adding Python 3 support. So Python 3, as you know, it's not compatible, and we started implementing Python 3 on top of our existing Python 2.7. So right now we support 3.2, and we are moving towards 3.3. We also worked a lot on NumPy. which is still not done, but it's mostly complete. So most of NumPy stuff should work, except when it doesn't. But no SciPy and no other libraries like that. So status. Python code should just work. You should be able to just install Python code and generally it should work. Most, maybe not most, but a lot of libraries support PyPy natively. We did put a lot of work into making interaction with C code possible. So have you ever tried writing CPython C extension? Who did? Few people. It's a pretty difficult task to do from scratch and get everything right. We provide a layer for compatibility with that idea, but it works. It's slow and kind of works, except when it doesn't and crashes and segfaults and is really not recommended. And we invented something called CFFI, which is yet another way of calling C, which is, I think, a lot better. Armin will talk about it later. And we added something called CPPYY, which is a layer to interact with C++ code developed by people from Lawrence Berkeley Lab, I think. Where is Vim working these days? One of those. It's based on work done by certain people to interact with C++ from Python. We also added a small native C API for embedding, which we are trying to improve, and that makes it possible to use PyPy as an embedded library, like, say, in UWSGI or stuff like that. In the meantime, people ported a lot of modules like PyOpenSSL, Pygame, PsychoPG to CFFI, so the problem of C extensions is slowly disappearing. We also run fundraiser, so Python 3 gathered roughly half of the funding we need. NumPy gathered most of the funding, but not all. And on top of that, we run fundraisers for software transactional memory, which Armin will talk later. And I would like to thank everybody who donated. It's quite a bit of money if you think about it. We also started offering commercial support. So essentially, you have a performance problem, you call us, we'll try and fix it. We'll write benchmarks for you, we'll try to improve your performance or switch to PyPy and make it magically happen. Depends on the details. So Armin will talk about the recent developments.
Okay. So I'm going to talk about these two topics, CFFI and STM. So CFFI is a C foreign function interface. The goal of CFFI is to have an alternative to writing CPython C extension modules by hand. So it's an alternative to the CPython C extension, to C types, to Cython, for example. These are all other alternatives. Well, CFFI is more correct, more right than these alternatives, I would say personally. That's an opinion, right? Well, it is something that works on CPython and PyPy right now. It is fast-ish on CPython. It's super fast on PyPy. It's something that is actually being developed on Jython. And the basic goal is it tries to be simple instead of being magic. So it offers something that is very minimal. So yes, how standards proliferate actually. So yes, CFFI is a 15th solution basically. Yes, thank you. So, I want to show you a small demo, how it looks like. This is a demo, how you would call the C library GMP. I don't know if you know it. It's a library doing large integer manipulations. So, let's assume you need to use it, for example, because it's better than CPython's own long types for some reason. For example, well, for example, you have very, very large numbers or something like that. So you need, you use it, well, here this is a Python file, right? But here I open a triple quote and make a big string, and in this big string, I just look what's the definition of these functions that I want to call, like I want to call mpz add. What is its definition? Well, I look it up in the man page or whatever, copy and paste it here, and that's it. And this function takes mp int, like the type mp int. What is it? Well, it's some structure. So it's some structure. The details of the structure are not actually mentioned in the man page. So I'd say type def struct, and I use a colon, ellipsis here. Okay, it looks a bit magic. However, it's just very fast. Basically, you just copy paste the part of the C definitions of the library that you're going to call. You copy paste them here. Then you write a small FFI.verify part that contains a few extra things like the includes, which libraries to link with, all kind of standardish things, and you end up, well, that's it basically. You have the functions mpz add and the other functions, and you can call them here in normal Python. So for example, I need two variables of type mpzt. Okay, I get them with ffr.new. I need to call initialization of A, where I passing this string in base 10, B passing that other string in base 10. I need to call mpz add. Well, basically, this part of the code, this part here, looks like C. And well, just to show you that I did not lie, you execute it. Okay, yes, it takes two arguments and prints the sum. Okay, so the point of CFFI is that it is, well, C and Python are enough basically. You don't need to learn another language or variant like all the function of the C API of CPython, for example, or really another language like Python, or you don't need C types, which would require, I mean, how do you do the same thing in C types, for example? You can't, because you can't declare what is in the mp int structure. Well, you can make it opaque. Maybe it works in this case with some syntax tricks. So yes, so the basic idea of CFFI is to offer a completely minimal interface to C, and then you get something that is really at the level of C, and then if you have libraries that is a bit more complicated than GMP, and you want to wrap it in a Python interface in order for other people or yourself to use in a larger project, then what you usually do is you wrap it in some well, you use this FFI notation that I used. You put it in a local corner and hide it behind functions and classes that you write in normal Python. Yes, and so this is all. I mean, this is actually all inspired by LuaJIT's FFI interface. But one main difference is that one main difference is that this thing here actually use a C compiler under the hood. For example, to figure out what you meant when you use ... in the definition of a function of a structure, for example. So it uses the C compiler to figure out what exact size and where are the fields, for example. So it means that you have the same advantages as you would normally have when you write C, Python, C extensions. Okay, now I'm going to talk about something completely different, which works only on PyPy, and this is global interpreter lock. So the global interpreter lock, the GIL, well, the GIL problem is a problem that is well known in the Python community. It's a problem that if you have one program, you cannot in this program make use of more than one core, one CPU core. Because even if your program uses multiple threads, then all the threads are actually running only one at a time. And this is the case on CPython, and it's also the case on PyPy for the same reason, basically. So now this is an approach to solve this problem. So the main idea is that, well, this how should I say? This is a version. This is a version that well, it is not just a version of Python in which you don't have the global interpreter lock. It is a version of Python in which you as the programmer that is using it, you still feel that you have the global interpreter lock. It means you can still use all the good properties of the global interpreter lock. Like you know that you won't actually have two threads that run really at the same time and will like both try to modify the same object and the things will completely crash, for example. This is not possible in the global interpreter lock version, and it's not possible either in this STM version. So what we have is, well, STM free threading done right, basically. So it comes with some overhead. Like we have an overhead of typically 30 or 40%, which means that if you have one program running on just one core and you are using this special version of PyPy, that is PyPy STM, it will run 30 or 40% slower. However, if the program starts, let's say, 2 threads, and you have at least 2 cores on your machine, then they will actually run in parallel. So yes, the good point of STM is that the interpreter author, that's us, we can do it. I mean, with this PyPy STM is not done by taking the source code of PyPy itself and adding very carefully lock everywhere. It's not done like that. And it also means that you as a user, you can also take your program and you don't have to carefully add locks everywhere. You can if you want, of course. But the point is that you don't have to. So why is it called software transactional memory? Well, the idea is that it's a bit like a database. A database in which you are reading or writing to with transactions. So it's really the same idea of transaction. What occurs is that, well, if you have a system with a GIL, then you have 2 threads, but there is a GIL, so it means for a few byte code, only this thread can progress. And then it suspends, and the other thread can progress a few byte codes. And then it suspends, etc. This is the normal GIL model. So now the transactional model is the same, but these few byte codes, you consider them as doing a transaction, but with respect to memory instead of the database. If you want, in other words, you have replaced the notion of talking to a database with really the CPU talking to the memory. So everything that the CPU tries to read or write from memory is done in a careful way that's similar to how a database would work. So the effect is that now if you have your two threads and each tries to run a transaction that is running a few byte codes, well, similarly to a database, they can actually both run at the same time, and at the end, well, at the end it depends basically. If both transactions did not actually create any conflict, then they are committing, and both have committed, and you have won basically. The time spent has been divided by 2 simply because the 2 transactions could run in parallel. And then only in some cases that we hope are not very common, then the 2 transactions will actually have a read or a write that conflicts with the others. So one of the 2 transactions will be aborted. And in this case, what it means to abort a transaction, well, you need to make sure first that everything that was done so far in this transaction is hidden, so thrown away basically, and then you restart the transaction from the start, from the beginning, from its beginning. So it's really the same idea as database, and the main difference is that, well, in order for this to work at a reasonable performance, we need to come up with very different trade-offs than a normal database, obviously. Yes. Mm-hmm. So yes, so as a summary, it's a way to get threading, but to get it simpler for the user, because if you have 2 threads each running a transaction, it behaves as if the transactions were actually serialized, meaning you first do one and then the other. So the fact that they can actually run in parallel is completely hidden to you as a programmer. And then there is also another trick, which is you can control the length of the transactions. Like if your 2 threads would acquire some global lock, like the same lock, so both threads acquire the lock, then they do things. So as long as they have the lock acquired, we consider what they are doing as just one transaction, then they both release the lock at the end. So it makes 2 transactions that can be longer, and I really mean long, like seconds of length. So the condition is that if these 2 long transactions are actually not conflicting, then they will be able to commit both. So it gives to the end programmer a very interesting alternative to write multiple threads, well, to write code that use multiple cores. The alternative is like this: you start multiple threads, and you run your code, which is divided into blocks, and every block can be large potentially, and you use one lock before you run anything in any of these threads. So basically you use multiple threads, but use one lock that will obviously make the threads run serialized again. So what did you gain? Well, obviously in the normal model you did not gain anything, and you would never do that. However, here it can work. Here it works because then every single sections of a query do stuff and release a lock. Even if it's the same lock, they can actually try to run in parallel. Okay. And I have here a demo. Wait. I have a demo somewhere. Yes. Sorry. Mandelbrot, yes. Run me. Okay. Okay, so this is running here. Here it's computing the image of a Mandelbrot set. It's not going to show it sadly, but you can believe me that it's computing it. So it takes some time. So this is running on top of a standard PyPy. Okay, it took 18.8 seconds. And now I'm going to run this very same thing, but using two threads. So I mean here it's just divided in horizontal bands, and I'm going to use two threads that each compute the content of the next band. So something simple. So 2. Okay. So this is running on my laptop, which has actually only 2 cores. Well, four if you count hyper-threading, but this does not really help. Okay, and this has took only 14 seconds, which is better than the previous 18. So you can see, yes, took only 14 real seconds, and about 25 if you make the sum of both cores simply. Yes, this is the overhead. So the overhead here is a bit like not completely, well, it can vary a bit basically. I have also other, well, I'm sure that if I run it again, I will get numbers like 12 and 22 or something. So yes, well, that's the point basically. And in order to get this result, I really had to change very little in the source code of Mandelbrot.py, and the point is that, well, the approach of multiple cores, the approach of STM should allow you to take a random program that has a few good properties, like it runs for a long time, and it has a few, well, it has blocks of code that you can more or less identify, and the actual execution of the blocks of code tends to be independent of each other. Like they don't have to strictly be independent, but they tend to be independent. So if you have a program with this kind of properties, then you can just use STM and it will be fast basically. So this is still a research project, and there are still a few limitations, obviously, but it's getting there.
Okay, so I should probably add that if that we are still looking for funding for STM. So Armin is working on this, and we have other people at ETH Zurich also working on this. So to change topic a little, what's the relationship between PyPy and our Python? So PyPy is not just a Python interpreter, it's also a framework for building interpreters. So we, yes, writing a Python interpreter that has a JIT is so hard, we prefer to write a framework for building ones and then build one, and was easier. We actually, it's very useful for writing VMs for virtual machines. So it won't work if you want to implement C or Java. Well, it could, but it wouldn't be as good. When we implemented in pretty record time languages like PHP or Ruby, I think getting like, I don't know, 60 or 70% of PHP tests, which is a lot because PHP tests cover like 500 million functions, took us something like 1.5 years with 3 people. So that, and right now it's a lot faster than standard PHP and essentially comparable with AHHVM, which took about 5 years, and they have a team of 30. So it seems that our Python is a decent way to implement dynamic languages, and has been used in a lot more like Prolog, Rocket, and some research stuff. Yep. I don't know. Software. So future. A few words about PyPy future. Just to quickly point what we are working on. Future is hard, and like I'm not willing to make hard promises, but we are definitely working on more general improvements. Especially the IO improvements are in the pipeline and are mostly done. We should merge it soon. We want to work on improving the warm-up time. I'll talk a bit about it later, and a bit about NumPy. So a lot of complaints about PyPy is that it takes forever to warm up and it eats too much memory. So this is something that I'm trying to tackle within, say, the next year. How to improve the situation, how to make JIT use less memory, and how to make it a lot faster to warm up. But again, then we have stuff like JVM, which takes even longer to warm up. So we are maybe not that bad. And we are looking for funding for the warm-up improvements. We are also working on NumPy. So NumPy is mostly complete, but most people complain that SciPy or Matplotlib doesn't work and they can't use it. We have hackish ideas how to attack the problem, and this one idea is to embed CPython inside PyPy using CFFI and just call it for SciPy. And that seems to work, actually. We have some demos with plotting from Matplotlib, so that's something that we're going to tackle on the sprint in Warsaw next week. That's pretty much it. You can find us here, you can find us online, and I'm going to take questions. Microphone.
I have a question about CFFI. So I'm actually using calling some C functions from Python, actually GMP, and I use C types for that because when I looked through the documentation of CFFI, I couldn't see what's the difference between CFFI and C types, and C types was available in the standard library. So what's the difference?
Where are you first? Okay. Well, so the difference, well, there is a small and a big difference. The small difference is that in C types you don't need to spend effort to learn the C types way and to rewrite every function declaration, every type, everything in a special C type syntax. That's a small difference. Then you also have the bigger difference, that is, in CFFI, well, the bigger difference is, it depends a bit, like if you are on Windows or not, strangely enough. CFFI is kind of semi-pointless on Windows, because there it is very typical to have a Windows library to come with a well-defined ABI. So it means it is something that takes this structure, and the structure contains these fields, and everything is very well defined in order, I don't know, in order to be callable from other languages than C. I mean, there are actually a lot of languages that are supported or used to be supported very well on Windows. The difference is that CFFI is more about the API level. So CFFI works very well if you have only some approximate description in the C sense of what you're trying to call.
Thank you. And also, can I have another question about STM? So last time I checked, I think it was like a year ago, maybe. And I remember that STM performance, this overhead, was still at this level, like 20% or something. So is there something fundamental that is blocking the progress to make it more efficient?
I just wanted to add to C-types that C-types has crazy magic that's like sometimes impossible to follow. It has rules that are not like C, but not like Python either. It will keep stuff alive and then randomly delete it, and it's really hard to follow. CFFI really tries to be like C. If you understand C, you will understand CFFI. With C-types, it's a bit harder.
Okay.
Yes, so the STM performance, well, the numbers 30% slower have really been coming only from the start of this year. I mean, the STM project is older, yes, started 2 or 3 years ago, but well, I mean, if you look at in the first proposals for STM, our goal was to have 2 times, up to 5 times slower. So we are already incredibly faster than originally promised or something.
Thank you.
Hi, Roman. My question is about STM as well, and you told that transactions in STM are kind of transactions in data, kind of serialized transactions in the database. And my question is whether it's possible to change the level of that transaction isolation in order to trade between thread safety and performance. So could I, for instance, set it to enable dirty reads and manage locking myself when I actually need that?
Yeah, no. I mean, the problem. Well, basically, the problem is that if you take an interpreter like CPython or the standard PyPy, and you just kill the global interpreter lock, and well, what occurs then? What will probably occur is that it will crash very obscurely because of concurrent access done by different threads, but not like the obvious things that you are doing from the language. So the problem of Python itself is that it's a very complicated language, and to do any simple operation, you actually need to read and write a lot of memory, a lot of fields and stuff and structures that exist in the process. So if you take a program and run it without any protection given by the GIL or STM, then well, you're going to crash the interpreter.
Okay, thank you.
I'm interested in your opinion why CFFI is the right way to do it.
It's the 15th one. Why is it the right way? Well, I mean, there are two reasons. One reason is that, well, it just looks better, in my own opinion. It's simpler. It does not add tons of any big layer that you need to learn in order to use it. So And well, so this is kind of one part of my answer, and the other part is that, well, it was much easier to make it fast on PyPy. So now any code using CFFI is actually extremely fast on PyPy. Like, you have the JIT compiled version of a function. So if this calls a C function with CFFI, well, you get inside of the compiled machine code the call to the C function directly. So you can't be faster, basically. Yeah. Yes, no, you cannot really inline the C function.
Okay. And I have a second question. Is there a way to make it work with not only C, but also other languages like Fortran or something?
It has been done. Like, it generally seems Fortran is compatible enough with C ABI that it wasn't a problem really at all. Fortran has its quirks, but then you obviously don't copy paste the Fortran code inside the CDEV, but you can write C prototypes that are useful for calling Fortran, and that works. We did that.
Thank you.
So yes, basically CFFI is really meant for calling C, and then, well, it is possible to write a C program that calls a Fortran library. So you need the same kind of hacks, basically. And same answer for C++ as well. Like, if you have a C program that wants to call a C++ library, then yes, it is possible. I mean, it's not obvious. You need to, well, I don't need to tell you, basically. If you have this problem, you already know. But the problem and the solutions are exactly the same with CFFI.
My question is, will it be possible in some reasonable time to use PyPy to generate ASM.js code? Because there are some projects to allow it. Will it be possible to create, the production grade web applications that would access DOM, that would handle all the events, or is it, or it would simply it wouldn't happen?
So how do you access DOM from ASM.js? That's the first question.
I know you can't access directly from ASM.js. You need to call JavaScript code from ASM.js, the pure, not optimized JavaScript.
So essentially, it's possible to have a special backend for PyPy to compile to either JavaScript or ASM.js, but the platform is so bad it will never work as good as you want it, essentially. Like, yes, ASM.js is allegedly like, I've seen benchmarks where it kind of works if the code is simple enough, and then it turns out if the code is not simple enough, it slows down by like 100 times. And that's not good, because that's like untranslated PyPy. Like, PyPy is a Python program, you can run it on normal C Python, and then you compile it, and then it's like 60 times faster. So you didn't gain anything. You're like, your platform is immature enough. So the problem is not on the PyPy side. From the PyPy side, you can compile stuff like that without too much trouble. But the JavaScript as a platform is really bad for this sort of stuff. You can only reasonably compile stuff to JavaScript if it's like JavaScript except has different syntax.
Thank you.
Yes, well, the recent problem with as well is just need to wait for the next generation, and then it will be solved, I guess. But the problem of hardware transactional memory, why am I talking here about software transactional memory? It's because there is also hardware transactional memory that exists. But the problem of hardware transactional memory as implemented today is that they are not supporting long transactions. And by long transaction, well, it's there are at least 2 or 3 or 4 or more orders of magnitude longer transactions in PyPy STM than supported by any HTM that exists now. So no.
Okay, so we have time for one short question.
Hey, so I'd like to ask you about the transactional memory management system. So if we have lots of threads that are concurrently trying to access the same resource, you've said that all of them, or all of them except for one, will abort to avoid conflicts, or am I?
No, that's right.
Yeah.
I mean, it's really similar to a transaction. If you have
Yeah.
2 different threads that all read the same memory, they don't conflict.
Yeah, exactly. So in that scenario, if they abort and retry, abort and try, abort and retry, is it true that the overall performance will be actually worse?
Yeah, and well, in theory, it should not be worse because there is always one of the transactions that will succeed. So in theory, the total performance in real time should be the same as if you had just the global interpreter lock.
Okay, thank you.
But well,
Thank you.
I mean, that's not the case in practice. Like you have a lot of overhead a bit all over the place. But
Okay, so thank you.